This is chapter 4, where we will be drawing graphs of the trig functions. In the first two sections, we're going to be graphing sine and cosine functions. We can use these to describe the change in temperature or tides or the amount of daylight because they are predictable patterns. Let's go through the first few parts of this section. These are periodic functions because they repeat over and over again. So do you remember how we had coterminal angles? And when we're finding trig functions of coterminal angles, if the angles are larger than 360 degrees, we could just keep subtracting multiples of 360 till we got an angle between 0 and 360, and then we could find the trig function value. And this is because the functions repeat over and over again. Do you see how, if we look at the unit circle over here to the right, once you hit 360, then it's going to repeat. And 360 is equivalent to 2 pi, so after every 2 pi, the function repeats. A periodic function is a function that repeats, and for these functions, it's going to repeat after every 2 pi. The circumference of a unit circle, we know that it's 2 pi r. If the radius is 1, then the circumference is 2 pi. So the least value of p, for which sine and cosine repeat, is 2 pi. Therefore, the sine and cosine functions are periodic functions with period 2 pi. When we write the sine function of x, so sine of x, this is the same thing as taking sine of x plus n times 2 pi, where n is some integer. So if we wanted to find sine of x, it would be the same thing as sine of x plus 2 pi, or sine of x plus 4 pi, sine of x plus 6 pi, or you could have n be a negative number. So if you add or subtract 2 pi or some multiple of 2 pi, you're going to come back to the same function. Same thing with cosine. Whenever we add or subtract a multiple of 2 pi to the x, then you'll have the same function back. If we go back up to this definition, the periodic function is the function f such that f of x plus np is the same. That means it just repeats after a certain value of p, which in this case is 2 pi for sine and cosine. So all of this means that sine and cosine will repeat after every 2 pi. Now let's see what happens if we look at the unit circle when the s, so now instead of calling this x, we're calling s, as s goes from 0 to pi over 2. Well, this is in the first quadrant, and so remember how sine of s is equal to the y value from the previous chapter? And cosine of x is equal to the x value. So what I'm going to do is look at the y values first for sine. And remember, those are the y values here. If you look at the unit circle, what is happening to the y values? Well, the y values are going from 0 up to 1. So the y values increase from 0 to 1. What's happening to the x values? Well, the x values, they start at 1, and then they go down to 0. And so this decreases from 1 to 0. In the second quadrant, which is pi over 2 to pi, what happens to the y values? Well, they go from 1 down to 0. And then for cosine, what happens to the x values? The x values go from 0 to down to negative 1. From pi to 3 pi over 2, that's in the third quadrant. What happens to the y values? We go 0 down to negative 1. So the x values go from negative 1 to 0. Then for sine, from 3 pi over 2 to 2 pi, that's in the fourth quadrant. You can see also the radians are labeled here, 3 pi over 2 up to 2 pi. The y values go from -1 up to 0. And then the cosine values, which are the x's, go from 0 to 1. If we look at the sine of s in general, going from 0 to 2 pi, you can see that it increases from 0 to 1, then it goes back down to 0, goes down to -1, and then back to 0. For cosine of s, looking at the x values, they start at 1, going down to 0, then down to -1, back up to 0, and then up to 1. Now let's look specifically at certain points between 0 and 2 pi. Going to the sine function. Okay, for the sine function, we have f of x is equal to sine of x. We are going to replace, if you remember, we had theta, sine of theta. Now we have sine of x. So if you remember, the definition of sine is y. So it just happens to be y up here also. We're going to go to the unit circle and find the y values when the angle is x. So when the angle is x, what is the y value of the ordered pair? The angle is 0, the y value is 0. If the angle is pi over 6, the y value is 1/2. The angle is pi over 4, the y value is √2 over 2. The angle is pi over 3, then it's √3 over 2. And if the angle is pi over 2, we have a y value of 1. Now skipping around a little bit, we have pi for the angle. Y value is 0. If the angle is 3 pi over 2, the y value is -1. And at 2 pi, the y value is 0. If we plot these points, we'll have 0, 0. And then pi over 6, 1/2, well, that's somewhere in here. Pi over 4, √2 over 2. √2 is equal to 1.4 divided by 2 is about 0.7. That's up here. Pi over 3 is √3 over 2, so that's 1.7 divided by 2, somewhere around here. And then pi over 2 is 1. So you see it reaches a maximum at 1. And then at pi, it's 0. 3 pi over 2 is -1. And then at 2 pi is 0. And this is a continuous function. It just keeps on going, repeats over and over after every 2 pi. If we look at just the part that's between 0 and 2 pi, just this piece here, we can see that little piece is going to repeat over and over again. The domain of the sine function is -infinity to +infinity. Because the domain, remember, we read from left to right, it's the set of x values. The range is a set of y values. The lowest y is -1. It includes it. And the highest y value is 1. We read the range from bottom to top, so from -1 to 1. The graph is continuous. That means that when you draw the graph, you never lift your pen from the pencil over its entire domain. You just keep on going without lifting your pencil from the paper. That means it's continuous, and that's over the whole domain, which is -infinity to +infinity. The x-intercepts have x values of the form. Let's look at the graph. It's 0 for the x-intercept, pi at 2 pi. So you see how they're just integer multiples of pi? So we can call this n pi for the x-intercepts. Its period is how far does it go before it repeats. So do you see how it's going to repeat after every 2 pi? It's a periodic function that repeats after every 2 pi. The graph is symmetric with respect to origin. So the function is an odd function. And for all x in the domain, sine of negative x is equal to negative sine of x. The graph is symmetric with respect to the origin means that if you have the point pi over 2, 1, then the point negative pi over 2, negative 1 is also on the graph. The sine function is related to the unit circle. Its domain consists of the real numbers corresponding to the angle measures, and that's what we found in our table. And its range corresponds with the y coordinates of the unit circle, because sine of x is equal to y. Page 3, 4-3, we have the graph of the cosine function. The graph of the cosine function is the graph of sine shifted or translated pi over 2 units to the left. Let's see how that's the case. To plot the points, remember that x is going to be like our angle, and then remember how the cosine by definition is equal to x. And so when we're given these x values, like 0, this 0 refers to the angle in radians. So that would be this 0 here on the unit circle. But remember the definition of cosine is x, and so this y value that we're finding for cosine is actually x in the ordered pair. When the angle is 0, the x value of the ordered pair is 1. That's cosine. So remember, that's the definition that we found in chapter 3 of cosine. If the angle is pi over 6, then the x value is root 3 over 2. If the angle is pi over 4, the x is root 2 over 2. So we're finding the cosine values for these angles. If x is pi over 3, then cosine is 1/2. If the angle is pi over 2, cosine is 0. The angle is pi. Cosine of pi is -1. The angle is 3 pi over 2. Cosine is 0. And if the angle is 2 pi, cosine is 1. We could plot these points. Here we have 0, 1. And I'm just going to go to the minimum and maximum points just to make things easier. You could plot all these points in the middle. And then at pi over 2, we have 0. At pi, -1. 3 pi over 2, 0. And then 2 pi, 1. And so we have a smooth curve that passes through those points, and you can see that cosine repeats after every 2 pi, just like sine. The domain of cosine is -infinity to +infinity. The range would be from bottom to top, goes from -1 to 1. The graph is continuous, it just keeps on going over its entire domain, which is all real numbers. The x-intercepts have the form 2n plus 1 in parentheses times pi over 2, where n is an integer. We look at the graph. Do you see how the first x-intercept is pi over 2? And then if we add pi to that, we end up at 3 pi over 2. Add another pi, we come up with another x-intercept. Well, if I distribute this pi over 2 to each of these, this is the same thing as pi over 2 times 1, which is pi over 2, plus pi over 2 times 2n, which is pi n, or n pi. So this is the same as this one here. I think this is a little more understandable. We start at pi over 2, and then you can just add or subtract any multiple of pi to come up with another x-intercept. Its period is 2 pi. That means it repeats after every 2 pi. This graph is symmetric with respect to the y-axis. If we fold it over the y-axis, you can see you get the same graph. So it's an even function, and that means that for all the x in the domain, cosine of -x is equal to cosine of x.